Alright.
You decided to go quick there last minute.
You could tell it was last minute too, because he slammed on his brakes at that stop sign. It's kind of funny.
Alright. Let's get the 10 minutes.
What is it? Common order? Yeah.
Okay.
Yeah, I'll just start in a second. Oh, yeah.
No.
Did you think
Does,
about
does
Okay.
it, does it look like?
All right.
No, completely.
We'll get started. We only have a few things to cover. I'm going to give you some time to work on your assignment, the one that I gave you yesterday.
Awesome.
Only had 10 problems. Let's do tomorrow. I want to give you some time to work. I know we're out of here at what, 9:01, something like that, so we have a shortened period. It's Wednesday. All right, big thing today. I want to review products. You know, either Pascal's triangle, which Abby, like very kindly yesterday, took 2 or 3 minutes on the end of the day, wrote out Pascal's triangle like 17th. She was bored, she came in here, she was watching chess. But I'm gonna leave that out there for a little while. I know it's overkill for what we need it for, but you can see the numbers, like you can see how big these numbers are getting. You're already in like the 19, 20,000s, and that's only 17th line down. And that's the number you have to multiply by, so it's gonna go even bigger than that. Goal today, I wanna talk about products and how to use the stuff we were doing in the homework for like an actual practical use. We use it in geometry quite a bit. Not the geometry that you guys had, but upper level geometry. And the type of problem that we would use it for would be something like this. This would be the idea. This is the type of problem, and I'm going to shade this in so you can see this. Okay, the question is to find the area of the shaded part. Find the area of the shaded part. This problem requires products, adding and subtracting, like all together. So, on all that stuff. So the idea is like why you'd ever do something like this, like the practical use for it is, let's say you're going to install a deck in your backyard. You're going to put in a new deck, you're going to put a pool in the middle of it. The idea is that if you're going to install a pool, you have to cut out the part out of the deck, right, to install a pool. So maybe you're going to get a bunch of lumber and wood that actually can make that deck. Well, here's the idea. By knowing the area of the deck, so you're going to subtract the pool out of the middle, just knowing the area, that can help you estimate how many boards you'll need. Because a board, you know, a 2x4, whatever you're going to use, whatever type of lumber, whatever size you're going to have, that has an area to it. So if you know the area of the whole deck, you can divide by what the area of one single board is, and that tells you how many boards you probably only need to buy. That's the practical use for it. Some people just don't think about that. Like, you can get a bare minimum cost you're going to need. Now, obviously, you're going to need more. You're not going to use like weird half boards everywhere, because you'd be cutting them up everywhere if you're doing it like this. But the idea is it can give you at least an estimate, which is nice to know, okay, what's it going to cost roughly? What's how many boards do I need? Where should I go? What type of wood? And that type of thing will affect what you're having. So most people aren't just going to go out buy the wood and try to just build it. That's not practical. You have to come up with a design and come up with some blueprint. Well, this is the start. You can estimate cost. Maybe it's going to cost you $5,600 to do it, and you're like, I don't want to spend $5,600 on a deck. So you're going to try to change the design. Maybe we'll put the pool on the outside, not on the inside, so it makes it easier. You don't have to do as much cutting. You can use less lumber, that type of thing, because you can push the deck in a different spot, or the pool in a different spot. But let's do this problem, just so you can see this. This is my one practical use problem. So to find area, do you agree that there's 2 rectangles in this picture? Yeah, 2. There's the big deck and then the pool in the middle. In fact, let me just put the pool here. There's your water. All right. What we're gonna do, we're gonna find area of both. So we're gonna find the area of the big deck overall. So the area of the large space is you take the length times width. That's how you find area of a rectangle. Throughout this year, we're gonna talk about area and volume and all that stuff, because we have to apply it, so volume will be the next type of problem we'll do. But we have area is length times width. So the idea is that length width, it doesn't really matter which one's length and width, but you're gonna multiply them. So for the big deck, I'm taking x squared, and I'm taking it times x plus 6. That's the area of the overall deck, that entire thing. That's including the pool, because that's everything, length, width. And then what we're gonna do is we're gonna subtract the area of the pool. That'll get rid of it, so I can just figure out what the lumber I'll need. So the area of the pool is the x times x plus 3, times what? So you can see there's a product in there, and there's some indifference in there. It's got everything. It's a mixed bag of every single type of problem. So it's guaranteed on the next assignment we're gonna have, this will be a part of it. You're gonna have some of these. I'm gonna give you just a few, maybe 4. I have 4 of these. So you have 2 of these, you have 2 of the volume problems. But it's pretty straightforward. So to do this, we're gonna have to multiply it. Let me use green here. So we're gonna take x squared times x. What do we get?
X cubed.
X cubed. X squared times 6.
6x squared.
6x squared. Good. There's the first part. Now, back here, I know we're gonna have to subtract. I know that. Okay? Good. You guys get checked in the office?
Yeah.
That's good. All right. So, we're gonna distribute the x through the parenthesis in the back. So we're taking x times x, which is x squared, and x times 3, which is 3x. But here's the problem, you still have to distribute the negative sign. A lot of people forget that. You have to distribute the negative sign because we have to actually subtract everything there. So what we're gonna have, x cubed plus 6x squared minus x squared minus 3x. And now we can combine like terms, you can go down, you can figure out this is gonna be a degree 3 polynomial, and we can go from there. Questions, comments about the style of problem? That's area, taking out the pool out of the center, and it's applying with the math we were learning the last, couple days. I'm gonna leave that up there, so now it's watching. Next thing, let's talk about, questions.
Why doesn't the minus sign go with the x to distribute to negative?
Right here, like, when you distribute it like that?
Yeah.
Yeah, I did that. I just did
Oh.
it second. Yeah, I mean, if you did it all in one swoop, you'd have been like, you just distributed the negative x through, you would have skipped the green line and just went right there. So that's good, yeah, you can do that. Yep, that was good. Any other questions? That was really good. All right, let's go to volume. Okay, volume problem. So this one's gonna be really bad. I'll try to draw the picture and I'll show you what I'm talking about with like a little model in front of you. All right. Okay. I did the best I can to draw 3-dimensional, it's kind of hard. Imagine you're looking at like a Jenga tower. Tower of bricks, right? You're missing the brick in the top and the middle. So it's missing this one brick right here that's sliding in. We're gonna try to find the volume of this thing. Volume of it. The actual tower without the Jenga piece that's sitting up there. This is probably the more difficult out of the two problems. Because now you gotta think about volume, what volume is, and you have to consider what dimensions they're gonna give you on the picture. Now, does everyone kind of understand the picture that they're looking at? Get the idea what it is? Okay. Because, it's hard to see 3-dimensional, especially when I'm doing a really bad job of drawing. But the dimensions you'll need when we find volume of something. So volume of a rectangular prism, that's what they call it, or a cube. You take the length times the width, so it's kind of like area, but then you take it times the depth, like how far back it goes. So it's still the same thing, length, width, and how far back you go. So let's give some dimensions here. Let's go, this is an x plus 3, this is an x plus 7, and the height, let's call this an x plus 1. So there's your 3 dimensions of this overall object, right? Big object. Length, width, and depth going back is x plus 3. Over here, what they have here, they have a 3x and just an x. That's the length and width of that Jenga piece that's missing. Now, there's one thing you have to think about. Okay, this Jenga piece that's up here, it's x by 3x. the one dimension I'm missing is going to the back. You know, I have the length and width. What's the dimension going to the back for this Jenga piece? Yeah, it's the same number. You're absolutely right. Because the depth should be the exact same. This depth should be the x plus 3 up here. That's the depth going back for the Jenga piece that's missing. So, what you have to do, you have to find the volume of the big object, the overall thing, the huge thing, and then subtract the piece that's missing out of it. So the piece that's missing, or the big piece, taking all three, x plus 7, x plus 1, x plus 3. That is how you find volume for the overall shape, the big tower. But I have to subtract the Jenga piece. The Jenga piece that's missing is x, 3x, and the dimension going to the back is x plus 3. That's the piece going to the back. Does that make sense? The setup. How you find volume, and then you subtract the dimensions of the Jenga piece. Again, it's mixing everything we did yesterday with, practical use. Again, this is how you find volume for an object in, like, if you're going to be in fabrication and you're going to be, 3D printing an object, you might have to think about how much, matter you have. Do you have enough stuff to actually 3D print it? Or do you have to use a different design, a different template to make sure that, the materials you have can actually make that object solid? Yeah, there's a lot to it. There's a lot more than you think there is. But the overall object is, to find the volume, you have to actually FOIL it all out. Okay, questions? Does anyone want to see me finish that problem? Are you good and you get the idea behind it? Okay, I'm going to take silences. We're good. I think we can cover it. We're going to practice that more tomorrow, because this will be on the next assignment we have. So I'll try to remind you how to do that each day until we get that next one. Okay, we do have an assignment due tomorrow. Keep that in mind. That's page 53. All right, next thing I want to talk about, Pascal's triangle. Yesterday, Abby was very nice. She wrote this all up here. The one problem I have not covered is how do you actually do Pascal's triangle for a trinomial? I did it for binomials, right? But I've never shown you how to do it for a trinomial. I just want to do the setup so you can see this, how you can do it. Okay? All right. And I'm not going to finish this problem all the way out, but I want to show you how you can adapt it to something bigger, like a trinomial or a polynomial. Any size object, you can still do this triangle to. So let's make x squared plus 4x plus 3. We'll make that. That's our our trinomial, and we're going to put this to the third power. Okay, that's a lot of objects. In fact, if you're to actually multiply that thing out, you're going to have 27 things across the board. If you actually put your 3 parentheses next to each other, FOIL the first 2, FOIL the next 2, you're going to have 27 items, and then they'll simplify from there. That's a lot. Maybe it'll take you too long. Maybe it'll get lost in the middle, what you're supposed to be doing. So you can do Pascal's triangle to it. But here's the trick. You have to make it look like a binomial. Because binomials are how we did Pascal's triangle. So what I mean by a binomial, imagine that this, now I'm gonna say that this is W. I know this is gonna seem a little weird. I'll explain in a minute. Let's say that's W, and this is how I'm gonna basically look at this problem. That's how I'm going to look at it. I'm thinking like the back 2 items, the x plus 3, is just one item in the back by itself. It's like a digit, it's a number. So now what you're looking at is an actual binomial, and we can follow the same rules. So I'll still do Pascal's triangle, what is that, third row? A 1, 3, 3, and a 1. So I'll still follow the same pattern, like this. And we'll put each item behind them, and we'll put the powers counting down and counting up, because that's how Pascal's triangles work, right? So the 2 items, because again, I'm thinking of it like a binomial, where I'm going to use 2 items. So the first item is the x squared. The second item, well, that's W, right? That's the second item in these parentheses, so I always have to put it right here. But instead of just calling it W, I'm going to call it this. What is that? Oops, sorry. 4x plus 3. 4x plus 3. And that one, and we'll put powers on it. And each item is gonna get this. X squared, 4x plus 3. X squared, 4x plus 3. X squared, 4x plus 3. And then you do the same rules that you did earlier. You count down in powers, you count up in powers, and then you can finish out the problem. So, what's the biggest power in that parentheses? The 3. So it'll be 3 and 0, and then these x squares will count down, so 2, 1, 0. And the second parenthesis will count up, 1, 2, and 3. And then you go from there. So in the middle of that problem, as you're doing this, you're gonna have to figure out what this is, figure out this. Eventually you're gonna start to see, like, you're gonna have to FOIL this thing out. You're gonna have to FOIL that thing out. So there's another Pascal's triangle in there, if you think about it. You could, I would say that the numbers are small, you do it by hand, but if they get outrageous, you'll have to do it. That's why I kind of waited. I didn't want to show you that before getting that homework. That if you ever had a trinomial or a polynomial, something bigger than 3, you can still do this, it just makes it difficult. You can see, like, that's a tough problem. That would take a long time to finish. Okay, questions at all about how to apply Pascal's triangle to something bigger? I kind of hinted that we can do it, I just didn't show you up till now. All right, perfect. The last thing I want to do today is just intro what we're going to be going into, like, tomorrow and other things. This is just a light introduction. It's factoring. This is the part, it's not foiling, it's breaking things up. So factoring, pulling pieces apart on a polynomial, okay, or any type of polynomial. Now, all I'd like you to do is write down the types of factoring, the classifications of them. So this is the part that in Algebra 2, they don't do I don't think they do a great job of highlighting, like, what the different types of factoring are. So I want you to have these 5 types. There's 5 types. Okay. The first type. And this is the one that I always check for first. I kind of go in this order, basically. The first type I look for is anything that's called a common factor. Common factor. Common factors are when you look at a problem, you're going to try to pull out something that every item has in common. Something like this. 3x squared plus 6x to the third plus 15x to the ninth. What I would look at, if that was my problem, and I'm trying to factor this thing apart, you do notice that in that polynomial, it's actually a trinomial. They all have 3s, multiples of 3s, for the leading numbers out front, leading coefficients, and they all have x squares or higher. So you can pull out items that they all have, and you can pull those out, factor it out, and then you can go from there. So, factoring, it's trying to figure out what do you multiply together to give you that item. So you're going backwards. You're finding the dimensions of an object if you knew what its total size was. Or if you had so much lumber, what are the dimensions you can make on a deck? That could use all of it. That's basically what you're doing. Some people won't think of it that way. You're backing up. You're finding what things multiply together to give you that total area. So that one's a common. We'll talk about that. This is the one I always check first. It makes things a lot smaller when you pull out that common factor. Second type is just called the trinomial rule. Trinomials. This is the one that they probably spend the most time in Algebra 2 covering. A trinomial rule is doing this problem. X squared plus 4x plus 3. Knowing how to break it up into 2 parentheses correctly, put certain numbers in each, put certain symbols in each parenthesis. There's a lot of rules to it. I know, like is that kind of what most people, I know. And it's like painful when you start doing it. It's like, oh man, we have to do this over and over and over. I have a simple rule that I follow when I do mine, and it works every time. You don't have to, like, beat your head against the wall trying to figure it out. It just works. It gives you your answers pretty quickly. But yeah, that's the one that most people do in Algebra 2, is this one. And then they try to teach you all these rules, like perfect trinomial squares, and that's stupid. I have one rule that works every time. Okay? That's one we'll talk about tomorrow. Third rule. Third rule is a difference of squares. The difference of squares. That's doing a problem like this. X to the 8th minus 16. It's a binomial, not a trinomial. It has to be a binomial, and it has to be a difference, subtracting. and both items you're looking at have to be perfect squares. So like the items, you can figure out what multiplies together to give you each item. Like 16, what, 4 and 4. The x to the 8th is x to the 4th, x to the 4th. You can figure out what multiplies to give you that. That's the idea. So that's a difference of squares. Most people can recognize that one instantly. The fourth type is the one that most people always get wrong. It's like the most common one people make mistakes on is the cube rule. Cube rule. There's two. There's actually two cube rules. But this is the most common one that people make mistakes on. Problem like that. It looks like a difference of squares because it's a binomial. In fact, I could have a minus sign in there. It would look like a difference of squares. The problem is how I see the difference between a cube rule and a difference of squares. On a cube rule, the numbers have to be perfect cubes. 3 things multiply together to give you those. You can have a problem that it actually could be both ways. It could be a difference of squares, or it could be a cube rule because of the numbers. Okay? So, that's my low. But you could have both. And I'm going to show you that example tomorrow where you could do it either way. You'll see why you can do it either way because the problem will keep going. It's called completing the factoring. Factor completing. Final fifth type is the one that is the hardest to teach. It's the hardest, it's not hardest to learn, it's the hardest to show you examples of because there's just infinite options that they could have here. It's called grouping method. Grouping. Grouping method is when they do a problem like this. 8x plus 7, and we're going to go minus 16 plus, let's call this x squared, and I guess let's go like a 4x or something. Where what you can do is you can like group things together. That's not a great example, but you can group things together. Like there's usually 4 more items. You can group things together, and you can pull items that each of those things have in common out. And eventually, what could happen is that you could go further after that. You're not just doing everything at once, like not looking at the whole thing. You're picking pieces. Does that make sense? That was a terrible example because it won't go further after the first step. Questions at all about what we could be going into? Okay, this is just the intro day to show you kind of the rules we're going to be getting. The rest of the time is yours. You have about 12, 13 minutes here. You can work on page 53. It is due tomorrow. All of you are kind of working on that. Hand out some papers for people that turn in some stuff that they fixed to make corrections, all that good stuff. Remember, homework's due tomorrow. Don't forget.
Can we turn it an hour?
Yeah, well, yeah, if you're done, turn it in.